In this lesson, we will look at finding the area of a region that is bounded by a polar graph. So this is a deviation to something that we are already familiar with. For example, if we are back in Calculus 1 in the xy plane, and I give you two functions, a function f of x and another function g of x, and these functions intersect each other and create a region that is bounded between them, we know how to find the area of that region. We know that we would integrate from A to B, the regions that bound that, the x values that bound that region, and we would do the difference of those functions on the inside of the integral. Now that we have studied a little bit more in our previous lesson about polar functions, we're going to be finding the area in polar graphs. So in our first example, we're working with a rose curve. R is equal to 3 cosine 3 theta. I'm going to go back to our previous lesson. That does remind us of a graph like this that we have seen before. So I'm going to begin with just a rough sketch of what this rose curve looks like. It has a petal that is split between the first and the fourth axis. It has a petal in the second quadrant, and it has a petal in the third quadrant. These three petals are symmetrical, and we're being asked to find the area of one petal. It doesn't matter which petal we choose. We could find the area of this petal, or we could find the area of that petal. We'll talk a little bit more about which petal we'll work with, but just finding the area of one of those petals. We have a formula here that tells us that the area of one of those petals is 1/2 the integral from alpha to beta, I'll change those limits later, of the function squared. In this case, the function is 3 cosine 3 theta squared. And we're integrating with respect to theta. That means that these limits here are angles theta. So what we need to do is we need to determine which two angles trace through, because remember, as you trace these points, we get R values and we get theta values, and we plot them as polar points. At some point, as we trace through, we've reached one entire petal. It doesn't matter which petal we trace through. What we need are what are the angles that we used to get those 2 points that are at the pole. So to help us figure that out, I'm going to pull up my calculator. I've gone ahead and put my calculator into radian mode as well as polar mode. Now when I hit y equals, I can enter the function in terms of R. It is 3 cosine 3 theta. And then I hit graph. This is not a good picture, so I'm going to zoom in and I will see a better illustration of this rose curve. Notice I can see the blinking cursor there showing me that we are at the origin 0, 0. So right now we're right there. I'm going to hit trace. Now, when I hit trace, I see that, I'm not actually at 0, 0. Looked like I was at 0, 0. I'm at 3, 0. I can't see that point on here because my window is a little bit too small. You see my X max is 2.5. I'll change my X max to 3.5 and hit graph. Now I can see that point down there. So now when I hit trace, I can see that we start off, the first point that we get when theta is 0 is this point here, 3, 0. As we begin to toggle over, theta is then 0.13 and we're here. Remember, this is in terms of radians right now. So we're seeing fractional multiples of pi as these angles. That's what these decimals represent. Then we get a point over here, a point here, and then we get a point at the pole. So far, those points are not tracing through a petal on this rose curve, right? As we continue to toggle through, now we're here. We're at a point down here. You may want to adjust your window. I'll make my X min value a little bit smaller. I'll make it -4, and I'll make my Y min -4 as well, just so I can see a little bit more as I trace through. Now I've gotten another point down here. I'm going to continue to get more points. Notice that these points down here are tracing through an entire petal, and I've gone back to the pole. So we just saw an illustration of this petal here in the third quadrant being traced through. The angle that we ended at was the 1.57. I'm going backwards now to get the angle that we started at. The angle that we started at was a 0.52. I'm looking at what theta is, because remember, those are the numbers that I need to put in here to integrate in terms of theta for the angles that bound one petal of this rose curve. Now, we don't have the exact values. You may recognize that 1.57, that is an approximation for the exact value of pi over 2. I'm going to show you how you could quickly figure out what the exact values are. Just as a little caveat, if you're looking at the calculator and you see these x and y values, that e negative 12 and e negative 11 is a computational error in the calculator. If you move the decimal 11 places to the left, you basically have 0. So now, to show you how we could confirm exactly what those values are, it's tricky to tell because they're in radians. So I'm going to just switch to degree mode. But you have to be careful when you switch to degree mode, because remember that your window is still in radians. So if I'm in degree mode, I would want my max theta to be 360 degrees because it was 2 pi. So I'm just converting everything back to degrees. I'm just going to step by 1 degree at a time. And now when I hit graph, I still see the rose curve. But now when I trace, I'm seeing angles in degrees. 1 degree, 2 degree, 3 degree, 4 degree, so on and so forth. I don't want to go so slow, so let's just jump to 30 degrees. Oh, we have jumped to the origin. If I go back a little bit, okay, so at 30 degrees, we start off at the origin. So this 0.52 is really the exact value of pi over 6. That's the 30 degrees. I'll show you. Just notice as I continue to trace through, 50 degrees, 60 degrees, so on and so forth. I've already said that 1.57 was pi over 2. You'll see 90 degrees is the angle that completed that petal. So we're integrating from 30 degrees to 90 degrees, but we're going to do it in terms of radians. So we're integrating from pi over 6 to pi over 2. So I did all that to show how you use your calculator to help you determine these limits of integration in polar coordinates. And now we have an integral set up that we do know how to evaluate. So this lesson is really about conceptualizing these polar graphs, being able to find these limits of integration, which, mind you, are angles, and then you will arrive at an integral. You have set up an integral that you already know how to evaluate. So I'm going to go ahead and start evaluating this. I have a constant of 1/2 in front. Mind you, I need to square this 3, which will give me 9. So I have a constant of 9/2. I'll go ahead and pull that 3 squared out. We're integrating from pi over 6 to pi over 2. I've already dealt with 3 squared. So we have a cosine squared 3 theta d theta on the inside of our integral. We have seen integrating trig functions to different powers before. We looked at that back in section 8.4. We talked about different techniques on how to integrate powers of trig functions. Specifically, when we are integrating an even power of cosine, we need to use a power reducing formula. We did the same if we were integrating like a sine squared. So the power reducing formula, I'll go back to section 8.3. I think I said 8.4, 8.3. This one here. Only difference is right now we're integrating cosine squared 3 theta. So applying this formula, I would have 1 plus cosine. Be careful on the inside here. This was just x, but we have 3 theta. You have to double it in the formula, so this would be 6 theta, and the denominator stays 2. So now I'm going to go and replace what we had on the inside with this expression here. And we're still integrating with respect to theta. I'll go ahead and pull out the 1/2 that's in the integral from the 2 in the denominator. And now we integrate. With respect to theta, we will need to use a u sub in here. Think about u and du. We'll have to get a 1/6 to account for the 6 theta on the inside of that cosine. And the integral of cosine is sine. And this is evaluated from pi over 6 to pi over 2. Begin by plugging in my upper limit of pi over 2. 6 times pi over 2 would be 3 pi. Mind you, sine of 3 pi is 0. And now we subtract and plug in our lower limit of pi over 6. Make sure you distribute the negative when you plug it into the second term. Sine of pi is 0. You're left with 9/4 multiplied by pi over 2 minus pi over 6, which leaves us with a final answer of 3 pi over 4. In our second example, we want to find the area of the region lying between the inner and outer loops of the limacon, r equals 1 minus 2 sine theta. Let's go look at what that graph looks like. Here is what a limacon with an inner loop looks like. So something like this one. To get a better idea, I'm actually going to graph, because notice that here it's not clear if this is with sine or with cosine. I just know it has that kind of shape. I can see the inner loop and I can see the outer loop. And if we're finding the area of the region lying between, we would be looking for kind of that region, well, between the inner loop and the outer loop. In here. Because, mind you, here's the inner loop. And here's the outer loop. So the area in between the inner loop and the outer loop is the area that's shaded in black. But let's get a better idea of what this polar graph looks like by graphing it. I'm already in polar mode. I'm going to graph 1 minus 2 sine theta. I did not change my window or anything from the previous example. Conveniently, that worked out for me. I'm going to hit trace. One, I'll just give a rough sketch of what this looks like on here. We have an inner loop, and then we have an outer loop. So when we hit trace, we start off at the rectangular point 1, 0. So we get a point right here. I'm going to begin to toggle through. Remember, I have this set to degree mode right now. The inner loop starts at the origin. Looks like I get to the origin when I'm at 30 degrees. Or at least, I don't know if it's the inner loop. I know some loop starts at 30 degrees. So there's 30 degrees. Let's continue to move. We are, in fact, on the inner loop. Let's see what happens when we get to, say, 55 degrees. We're there. What about 60 degrees? I'm just continuing to move along this inner loop slowly but surely. I'll jump to 120 degrees. I'll jump to 180 degrees. I've gone too far. Let's go back to 130, 150. 150 degrees, we have gone all the way around. So we were looking at points that were doing this. And when we got back to 150 degrees, we had finished tracing the inner loop. We traced through the inner loop from 30 degrees to 150 degrees. Now let's see, as we continue to trace through the curve, 150 degrees, larger than that. We're now on the outer loop. Okay, so now I am looking at angles. I've traced through, I'm looking at angles that are now forming out this outer loop from 150 degrees. Let's jump to, say, 180 degrees. We're just still here at the -1, 0. I'll jump to 270 degrees. Oh, 270 degrees, I'm down here. Let's see where we are with 310 degrees. We're over here. Let's see where 360 takes us. Takes us to 1, 0. We're not all the way back around yet. Let's see where 375 takes us. Oh, we're getting an error now. And the reason that we're getting an error is because our window is maxed out at, because if you hit go to, it'll show you where the error is. The 375 is the problem. It's blinking on the 375. Our window is maxed out at 360. But on our graph, when we trace 360, we have not finished the outer loop. When I trace 360, I'm just right here, right? We started this outer loop at the same 150 that the inner loop ended at. So we started getting points over here. We've gone this far around. We're at 360. We haven't finished this little bit of the outer loop. So what I'm going to do is I'm going to expand my window. I'm going to adjust my window. Let's take it up to 420 degrees, let's say. Now that I have a larger window, I will hit trace again. I'll go back to 360. I can see that's not large enough. We had tried 375. We got an error. Let's try 375 again. We're still not there. As I continue to push through, I see that I land back at the origin at 390 degrees. So the point where that ended on the outer loop was 390 degrees, and the outer loop started at 150. That's important because now we know what numbers to use for our limits of integration. 390 degrees is 13 pi over 6. 150 degrees is 5 pi over 6. And 30 degrees is pi over 6. So now, thinking big picture, if we're looking for the area that is in between the inner and the outer loop, what we need to do is we need to find the area in the outer loop and then subtract from it the area in the inner loop. So I'm going to begin by finding the area in the inner loop. Formula tells me that is 1/2 the integral from alpha to beta. Our alpha to beta is the 30 to 150, which is pi over 6 to 5 pi over 6. And then we need to take our function and square it. In this case, our function is 1 minus 2 sine theta. I'll square that with respect to theta. At this point, this is an integral that we know how to evaluate. It may be tedious, but we are able to evaluate that integral. At this point with this sine squared, we're going to need to use the power reducing formula again from 8.3. This time I'm using the one for sine squared. 1 minus cosine 2x all divided by 2. Leaves me with 2 times 1 minus cosine 2x. I'll distribute that 2. Oh, and I should really have a theta here. Instead of an x. And I was reminded by my variable for integration with the d theta on the end. I'll continue integrating this now with respect to theta. I'm getting 3 theta because I'm combining like terms of 1 plus 2. So I have a constant of 3 on the inside of the integral. I'll integrate the negative 4 sine theta to give me a positive 4 cosine theta, and I'll integrate the negative 2 cosine 2 theta term to give me a minus sine 2 theta. You may need to do a u sub on that to go through that integration carefully. And now I'll just apply the fundamental theorem of calculus. You should be able to work through that and simplify. There's quite a bit of work to get that this simplifies down to, well, not quite a bit, but a good amount. Pi minus 3 root 3 over 2. I did go ahead and write out what you would get when you apply the fundamental theorem of calculus. So there are 3 terms. This is what we get when we plug in the upper limit of 5 pi over 6. Make sure you subtract and distribute your negative. That last term is negative, so it ended up becoming positive when I subtract. This is what I get when I plug in the lower limit of pi over 6. This all simplifies to pi minus 3 root 3 over 2. So we have the area of the inner loop. Now we need to work and find the area of the outer loop. The outer loop area will be 1/2. These limits of integration were from 150 degrees, which is 5 pi over 6, to 390 degrees, which was 13 pi over 6. We are integrating the exact same expression. I'll go ahead and write the simplified version of it. In fact, well, one, I won't erase that. So I went ahead and just wrote the simplified version of the integral because nothing changes. The only difference is the limits of integration. So why I hesitated was really I could have just jumped to this part because we already know how that integrates. The only difference is that here we are evaluating it from 5 pi over 6 to 13 pi over 6. So again, something that is tedious, but ultimately that we do know how to do. I will show what you have when you apply the fundamental theorem of calculus. I went ahead and evaluated cosine. Now I'm plugging in my lower limit of 5 pi over 6. I'm going to go ahead and evaluate cosine at 5 pi over 6 again. It is a negative root 3 over 2. When I take 5 pi over 6 and multiply it by 2, we have 5 pi over 3. And all of this simplifies down to 2 pi plus 3 root 3. So now that we have the area of both the outer loop and the inner loop, we are able to find the area in between the two of them by taking the outer loop area, which is 2 pi plus 3 root 3 over 2, not over 3, 2, and subtracting the area of the inner loop, which is pi minus 3 root 3 over 2. Which leaves us with a final answer of pi plus 3 root 3.